Hi there, I welcome you to my YouTube channel, The Chemist Chemistry. In today's video lesson, we will be talking about contour numbers and type of contour numbers as the subtitle. Before we proceed to the main lesson, I want us to perform this task. Kindly like this video lesson and please don't forget to subscribe to my channel. And lastly, click on the notification bell for more video lessons. Thank you. Quantum numbers. What is even a quantum number? A quantum number describes the distribution of electrons in an atom. It also describes atomic orbitals and labels the electrons that reside in them. So, in a nutshell, all that I am trying to explain to you in this lesson is that a quantum number describes how electrons are distributed within an atom. In other words, electron configuration. Two, it also describes atomic orbitals. Talks about a specific atomic orbital in question. And also tells about the electron that reside in a specific orbital. We have four main types of quantum numbers. The first on my list is the principal quantum number or the primary quantum number. Then we have the second being the angular momentum or azimuthal quantum number, which is the secondary quantum number as well. Thirdly, we have the magnetic quantum number, and the fourth one being the spin quantum number. Let's proceed by talking about each type one after the other. The principal quantum number. It is denoted by letter N, and the principal quantum number has an integer values starting from 1, 2, 3, 4, 5 in that order, etc. This quantum number relates to the average distance between the electron in a particular orbital and the nucleus of that atom. So when you pick an atom, we've learned in one of our previous video lessons, specifically Rutherford model of the atom, we learned that according to Rutherford, the atom has a central core, and the name of that core is called the nucleus. And within that nucleus, we have the proton and the neutron, which are two of the subatomic particles. So what principal quantum number is about is that it relates, that is from the nucleus to a specific electron within an orbital of an atom. So the distance from the nucleus, which is the center of the atom, to an electron within an orbital of that same atom is what is termed as the principal quantum number. In other words, take note that from the nucleus, we have shells surrounding the nucleus. It is within a shell that an orbital can be located. And also, it is within an orbital that an electron may be found. Take note. So, electrons are found in orbitals, and orbitals are also found within the shell of an atom. I want you to take note of that. Therefore, the larger the value of n, the further the average distance of an electron from the nucleus of an atom. Hence, an atom having a principal quantum number of 2 has its electron located far or further away from the nucleus than an atom with a principal quantum number 1. So as I said, the principal quantum number talk about the shell in question. So if the principal quantum number is 1, we are talking about the first shell. And we all know that the first shell is closer to the nucleus than the second shell. So the distance from the nucleus to an electron within the second shell will be longer than the distance from the nucleus to an electron within the first shell. As simple as that. Let's see how this model can aid us to grab the concept very well. We have this model here. So this is an atom. We have the center being the positively charged nucleus here. Then we have the first shell represented by 1 in green color. We have this orange color represented by 2 being the second shell. We have the black color being the third shell, and then the purple being the fourth shell. Now, the principal contour number also indicates the main shell in which electrons are located. So, as we learned on the previous slide, that n represent the principal contour number. So when n is equal to 1, we are talking about the first shell, which is also known as the K shell. When n is equal to 2, we are talking about the second shell, which is also known as the L. 3 equal to the third shell, known as the N. 4 equal to the N shell, or the fourth shell. 5, so alphabetically, so from K, L, M, N, O, that is the fifth shell. So from O, P, the C shell, in that order. So kindly let's take note of that. All right. So the distance from the nucleus to the first shell being 1 is shorter as compared to from the nucleus to the second shell being L. At the same time, from the nucleus to the third shell being M is longer than from the nucleus to the second shell being L. And from the nucleus to the fourth shell being N is also longer than from the nucleus to the third shell being M. So what we are saying is that from the nucleus to an electron located within any of this shell, the relation between the two, that is the electron in one of these shells, and the distance that is from the nucleus to an electron in any of these shells is what is termed as the principal contour number. And as the shell number increases, the distance also increases. So as the shell number increases from 1, 2, 3 upward, the distance also increases. So from this, we can say that principal contour number is directly proportional to the number of shells. Why? Because as the number of shells increases, the distance from an electron to within a given shell to the nucleus also increases. All right, let's proceed to the next one, the angular momentum or the azimuthal quantum number. The azimuthal quantum number gives the shape of the orbital. In other words, it is with the aid of the angular momentum quantum number that we are able to predict or identify or come by the shape of a particular orbital. The principal quantum number n also helps us to calculate for the value of the angular momentum quantum number. Now, for a given principal quantum number, the value of the angular momentum quantum number will start from 0 and end at the number just before the value of n. So as we all know from the previous slide, that the principal quantum number starts from 1 upward. So 1, 2, 3, 4 in that order. So we are saying that the principal quantum number will help us to know the angular momentum quantum number. And the angular momentum quantum number, the value of the angular momentum number will start from 0 and end at the number before the value, before the principal quantum number in question. So now we have the shape of the s orbital here. We have the shape of the p orbital. We have the shape of the d orbital, and we have the shape of the f orbital here. Now we can all see that the s orbital or the s subshell is spherical in shape, is spherical, like a circle, spherical. Then the p orbital is dumbbell in shape. We can see that it's dumbbell in shape. Now looking at the d orbital, it looks like a clover leaf. So we term this shape as the clover leaf shape. the clover leaf shape. The clover leaf shape. Then we have the F orbital or subshell. Looking at it, it looked like just a tetrahedron. Very good. So we term it as a tetrahedral shape. So the F orbital is tetrahedral in shape. The D has the clover leaf shape. The P have the dumbbell shape, and the S having the spherical shape. Now looking at the S, we can say that it is non-directional, but the P is directional. In one of the subsequent slides, I will explain that further. All right, so let's proceed. The magnetic quantum number. The magnetic quantum number. So the magnetic quantum number determines how orbitals with the same size and angular momentum are oriented in space. That is the arrangement of same orbital. In other words, degenerate orbitals. We're talking about orbitals of same energy level. Okay, how they are oriented in space. For a given value of angular momentum quantum number, the magnetic quantum number has a value starting from a negative value of the angular momentum quantum number to the positive value of that angular momentum quantum number in question. So we have the P subshell here is dumbbell in shape, and we have three main orbitals within a P orbital. So each of the three orbitals is oriented along a different axis, specifically the X, Y, and Z axis. So looking at this one here, this is the dumbbell shape of the P orbital is oriented on the X axis of this X, Y, Z as plane. So since it is oriented on the X axis, we term this P orbital as px orbital. Why? Because the dumbbell shape of the p orbital is oriented on the x axis rather. So we term it as the px. Now here it is oriented on the y axis. So we term it as the py orbital or subshell or suborbital. Now here we have it oriented on the z. So we term it as the pz orbital. Yes. So don't forget, the magnetic quantum number talk about orbitals with the same size and angular momentum quantum number. Let's go back. We all know that the p orbital is having an angular momentum quantum number of 1. The s having an angular momentum quantum number of 0. Then the the d having an angular momentum quantum number of 2. And then the F having an angular momentum quantum number of 3 in that order. So the P, they all have the same angular momentum quantum number, which is what? 1, right? And so they have the same angular momentum quantum numbers. And then they have the same size because this shape is the same. There is all dumbbell. You get a point? Yes. But the orientation is different. So that is why we are saying that the magnetic quantum number determines how orbitals with the same size and angular momentum quantum number are oriented in space. Okay, this table will enable us to summarize the relation between the principal quantum number, the angular momentum quantum number or the azimuthal quantum number, and the magnetic quantum number. So we've learned that when the principal quantum number is n, which is n, and which starts from 1, when the principal quantum number is 1, the shell in question is k, which is the first shell. When it is 2, the shell in question is L, which is the second shell. When it is 3, we are talking about the third shell, and that shell is the M. When it is 4, we are talking about N, which is the fourth shell. All right. And we also learned that to determine the angular momentum quantum number, it is the principal quantum number that will aid us to do so. And we determine that by counting from 0 to the number just before the value of that principal quantum number in question. So here, to determine the angular momentum quantum number of a principal quantum number, which is 1, we have to start from 0 to the number before 1. And we all know that integers starting from 0. We don't, in between 0 and 1, we don't have any other integer there or any other value there. So the principal quantum number, which is 1 for the case shell, will have angular momentum quantum number being 0, because it starts from 0 to the to the number before 1. And we know that from 0, we don't have, in between 0 and 1, there is no value or integer there. All right. Now, when we come to the second shell being 2, we will start from 0 and end at value just before 2. And we know that in between, or from 0 to 2, the number in between is 1. So the angular momentum quantum number for a principal quantum number 2 will start from 0 and end on 1. For principal quantum number 3, we will start from 0 and end on 2. So 0, 1, 2. Why? Because we determine the angular momentum number by starting from 0 and ending at the number just before the principal quantum number, which is 3. So 0, 1, 2. Very good. So here the principal quantum number is 4. So 0, we start from 0, 1, 2, 3. That is where we will end, because we will end on the number just before 4, which is the principal quantum number. So when the principal quantum number is 5, we start from 0 and end at 4. When it is 6, we end at 0, and we start from 0 and end at 5. When it is 7, we start from 0 and end at 6, in that order. Now let's come to the magnetic quantum number. Now, we've learned from this slide that a magnetic quantum number determines how orbitals with the same size and angular momentum quantum number are oriented in space. And we said that for a given value of angular momentum quantum number, the magnetic quantum number has a value starting from negative of that angular momentum quantum number. Then it will end on the positive of that angular momentum quantum number. So let's see how to determine the magnetic quantum number from the angular momentum quantum number. So here we know that the angular momentum quantum number here is 0, and we don't have a negative or a positive 0. So the magnetic quantum number will just be 0. When we come here, the angular momentum quantum number, we have 0 and 1 for the second shell. So 0, we have just 0. Then under the magnetic quantum number for the 1, we start from the negative of that angular momentum quantum number and end at the positive of that angular momentum quantum number. We just learn that from here. For a given value of angular momentum quantum number, the magnetic quantum number starts from, or has a value starting from negative of that angular momentum number and then end at the positive of that angular momentum quantum number. All right. So here is 1. So it will start from negative 1, which is because the angular momentum quantum number is 1. So start from negative 1. From there, we move to 0, and then it ends on the positive, which is 1 of that angular momentum quantum number. Here, the third shell, we have 0, 1, and 2. These are the values for the angular momentum quantum number. So for the 0, the magnetic quantum number will be 0. For 1, the magnetic quantum number will start from negative 1, 0, and then positive 1. It ends there. Then for 2, the magnetic quantum number will start from negative 2 to negative 1, 0, positive 1, positive 2. It ends there. 0, 0, 1, negative 1, in that order. When it is 3, negative 3, negative 2, negative 1, 0, 1, 2, 3. So when we have another angular momentum quantum number being 4, then the magnetic quantum number will start from negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. When the angular momentum quantum number is 5, it will start, the magnetic quantum number will start from negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5. As simple as that. All right. Now, let's come to the type of orbital in question. So, we've learned that when the angular momentum quantum number is 0, we are talking about the S shell. When it is 1, we are talking about the P orbital rather. So when it's 0, we are talking about the S orbital. When it is 1, we are talking about the p orbital. When it is 2, we are talking about the d orbital. When it is 3, we are talking about the f orbital. When it is 4, we have the hg, in that order. All right, we learned that from this slide. So angular momentum equal to 0, we have the s subshell. 1, here angular momentum is equal to 1, we have the p, here it was equal to 2, we have d, here it's equal to 3, we have f, in that order. All right, so here is 3, we have the f, 2, we have d, 1, we have p, 0, we have what? The s orbital. Now, another thing that I want you to also take note of is that, so what you have to do here is that you write the orbital. So if the angular momentum is 0, then you know that is the s orbital. If it is 1, is the p. It is 2, it is d. 3, it is f, in that order. So you write the orbital. Then you attach the principal quantum number. So here we have 1 s, because 0 represents s, the s orbital. And then the 1 is telling us that we are talking about that s orbital is of the first shell. Principal quantum number 1. Take note of that. So you see we have the same s here, but what is the coefficient there is 2, telling us that it is of what? The second shell, principal quantum number 2. We have another s here, because the magnetic quantum number is 0, the angular momentum is 0, so specifically we are talking about the s orbital. The 3 there is telling us that it is on that s orbital is within the third shell, principal quantum number 3. Very good. So we have 4 here, fourth shell, 0 as angular momentum. Then we have 4s, meaning that s orbital is found within the fourth shell. Let's take note of that. All right, so when it is p, that is 1, we have 2p, meaning it's in the second shell. We have 3p, third shell, 4p, that is within the fourth shell, in that order. So we have d, 3d, that is, it means that it is in the third shell, 4d, fourth shell, in that order. 4f, meaning that that f orbital is in the fourth shell. Now looking at here, you could see that within the under principal quantum number 2, we have only 0 and 1, meaning that we have only s and p orbital or subshell within the principal quantum number 2, or the second shell. And then for the principal quantum number 1, which is the first shell, we have only s orbital there. Now coming here, we have 1, 2, 3, that is s, p, d, telling us that within the third shell, we have the s orbital, we have the p, and we have the d orbital. Now coming to the fourth shell, we have 0, 1, 2, 3, telling us that we have the s orbital, we have the p, we have the d, and we have the f orbital also in the fourth shell. Take note of that. Now, to know the number of subshells, you count the number of the magnetic quantum number. So here for the first shell, which is the K shell, we have only one magnetic quantum number, which is 0. So meaning we have 1 orbital there. But when you come to the second shell, we have 1, 2, 3, 4. We have 0, another 0, we have -1, we have +1, telling us that we will have 4 subshells. We have 4 orbitals within the second shell. So we have the 1 being the 2s, the s orbital, and then we have the 2p, and the 2p we know we have learned that they are degenerate. So we have the px, py, and the pz. So we have the s orbital being 1 orbital, we have the 2px, 2py, 2pz. So in total we have 4 orbitals within the second shell. Now when you come to the third, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Telling us that we have 9 orbitals within the third shell. So we have s orbital there. Then we have the p orbital, which is degenerate. So we have px, P, Y, and PZ, making 3, in addition to this making 4. Then the D, we have 1, 2, 3, 4, 5. So meaning we have D1, D2, D3 up to D5. So making 5 plus 3 plus 1, making 9. In that order, when you count here to, you get 1 here. Here is 3, making 4. Here is 5, making 9. And then here is 1, 2, 3, 4, 5, 6, 7. Right? Yes. So in total, we will get 14. 14. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right? Okay. Sorry. 16 orbitals within the 4 shell. So that is how we determine it. All right. I hope you are following and you are being blessed by these diagrams. Let's move on to the quantum, the 4th quantum number, which is the spin quantum number. The spin quantum number. Electrons are thought as spinning on their own axis as the Earth does. The spin quantum number describes the direction of a spin of an electron in its axis. The spin might be in the clockwise or anti-clockwise direction. Yes. So we know that from Pauli's exclusive principle, which is one of the principles that very soon we'll be talking about. That is one of the principles governing electron configuration. Pauli said that each orbital can accommodate a maximum of 2 electrons, and they must spin in an opposite direction. In other words, one must spin in the clockwise direction and the other being the anti-clockwise direction, or one must spin up and the other spinning down. So we have the spin quantum number having only 2 directions of spin. So we have the positive half and the negative half spin values. So if it is positive half, it means that spinning is up, upward spinning, spin up, and we term that electron as spinning in the clockwise direction. When it is negative, we term it as spin down, meaning that electron is spinning down or in the anti-clockwise direction. These 2 possible values means that 2 electrons can occupy the same orbital as long as they spin differently. So each orbital can take only 2 electrons. Even when we take the degenerate, which is like the P, the D, and the F, which are degenerate orbitals, because we learned that, or we just learned that for the P, we have the PX, the PY, and the PZ. So meaning they are together, but we have sub, so 3. Then for the D, 1, 2, 3 up to 5. Then the D, 1, 2, 3 up to 7. The F rather, 1, 2, 3 up to 7. Very good. So this means that each orbital, each suborbital, 2 electrons in there must have opposite spin, one spinning up and the other spinning down. So let's see. So this is an electron, and then we can see that this electron is spinning up with the arrow in the red arrow spinning upward, and then the blue spinning downward. So this is a spin down, negative half, spin up, positive. Then we can see that this arrow is moving in the clockwise direction, spin up. Then this one is spin down, moving in the anti-clockwise. In other words, this is moving opposite of this. So anti-clockwise spinning. So we can see this is an orbital, one electron spinning upward, the other spinning downward. So each of these arrows represent an electron. So we can see that it is an electron here, an electron, and an electron. This is a magnifying image of this, of that. So we have an electron here, we have another electron here. So this one is spinning upward here, upward, right? Clockwise, spin up. Then we can see the spin down anti-clockwise here, positive, negative. So this is an orbital we have one electron spinning down, another spinning up. Yes. So this is how electrons are to be arranged within an orbital, or how they are arranged in an orbital, and they spin in a clockwise direction. So in summary, these are the four main quantum numbers that we have. The principal, which talks about the distance of an electron from the nucleus. So this is an electron. So a distance from this nucleus to this electron, or a distance from this nucleus, from the nucleus to that electron, or from the nucleus to that electron. You see that as we move from the nucleus to a given electron in a specific shell, the distance is increasing. All right. Then we have the azimuthal, or the angular momentum. We talk about the shape of the orbitals. And then we have the magnetic. We talk about how they are arranged, or their orientation in space, the orientation of orbital. And then we have the spin that talks about the orientation of the electron spin, whether I spin up or spin down, clockwise or anti-clockwise direction. Don't forget to like, comment, and also subscribe to the channel for more video lessons. If you have any question or any compliment, please let's know it in the comment section. Stay blessed. I love you.